In this video, we will discuss what are minimum cost spanning trees. The topic of spanning trees is related to graphs, and graphs have many applications. For example, graphs can be used to represent a network of airports. In such a graph, the vertices represents the airports and the edges corresponds to the available flights between the airports. The weight or cost of the edge might represent distance or airfare or travel time. Computing the spanning tree helps us in finding all the possible or feasible choices for the connection between the vertices. Let G be a graph represented by G equal to set of vertices V and set of edges E. The graph G is a connected and an undirected graph. The spanning tree of graph G is the subgraph, that is a tree and connects all the vertices. So, the spanning tree of a graph G is a subgraph T of the set of vertices V and set of edges E dash if and only if T is a tree and V is the set of vertices in graph G and E dash is the subset of edges in graph G. Let us consider an example. Let us consider a graph G with 4 vertices 1, 2, 3 and 4 along with the undirected edges from vertex 1 to vertex 2, vertex 1 to vertex 3, vertex 1 to vertex 4, vertex 2 to vertex 3, vertex 2 to vertex 4 and vertex 3 to vertex 4. Then the spanning tree T of the graph G is a tree with all the vertices in G, that is vertices 1, 2, 3 and 4 and the subset of edges in G, that is a set of edges E dash with the edges between vertex 1 to vertex 2, vertex 1 to vertex 3 and between vertex 2 to vertex 4. Remember, the spanning tree of a graph is a tree. So, there cannot be any loops in the spanning tree. Now, this leads us to the following properties of spanning trees. All vertices of graph G are in spanning tree T. The spanning tree T is connected. The spanning tree T is acyclic, that is, there are no loops or cycles. The spanning tree is also known as minimal subgraph of a connected graph. A minimal subgraph is one with the fewest number of edges. Spanning tree is called a tree because every acyclic undirected graph can be viewed as an unordered tree. Now, the example which we have seen is just one of the possible spanning trees of the graph G. It is possible for a graph to have several different spanning trees. For example, we can construct another spanning tree of the graph G with all the vertices of G and the edges between vertex 1 to vertex 3, vertex 2 to vertex 3, and an edge between vertex 3 to vertex 4. There is another possibility of constructing a spanning tree of graph G with all the vertices of G and the edges between vertex 1 to vertex 2, vertex 2 to vertex 4, and an edge between vertex 3 to vertex 4. So, it is possible for a graph to have several different spanning trees. Actually, a single graph can have many different spanning trees. Now, if we look at these 3 spanning trees, we can observe that all the spanning trees have 4 vertices and 3 edges. This is because of the property that a spanning tree is a minimal subgraph G and is connected. Any connected graph with n vertices must have at least n-1 edges, and all connected graphs with n-1 edges are trees. The spanning trees has many applications. One of the application is if the vertices of G represent cities and the edges represents possible communication links connecting two cities, then the minimal number of links needed to connect the n cities is n-1. So, the spanning tree of G represents all feasible choices of connecting different cities using minimal number of links or edges. In practical situations, the edges have weights assigned to them. These weights may represent the cost of construction, the length of the links, and so on. So, the cost of the spanning tree will be the sum of the cost of their edges. So, if C, V, W is the cost or weight of the edge, then cost of the spanning tree is the summation of C of V, W for all edges of the spanning trees. So, if we consider the graph G and assume that the cost of the edge between vertex 1 and vertex 2 is 2, the cost of the edge between vertex 1 and vertex 3 is 3, the cost of the edge between vertex 1 and vertex 4 is 5, the cost of the edge between vertex 2 and vertex 3 is 6, the cost of the edge between vertex 2 and vertex 4 is 4, and the cost of the edge between vertex 3 and vertex 4 is 1. Therefore, the cost of first spanning tree will be summation of cost of the edge between vertex 1 and vertex 2, which is 2, plus the cost of the edge between vertex 1 and vertex 3, which is 3, and the cost of the edge between vertex 1 and vertex 4, which is 4. So, the total cost of the spanning tree will be 2 plus 3 plus 4, which is 9. Then, the cost of the second spanning tree will be summation of cost of edge between vertex 1 and vertex 3, which is 3, plus the cost of edge between vertex 2 and vertex 3, which is 6, and the cost of edge between vertex 3 and vertex 4, which is 1. So, the total cost of this spanning tree will be 3 plus 6 plus 1, which is 10. Then, the cost of the third spanning tree will be summation of the cost of edge between vertex 1 and vertex 2, which is 2, plus the cost of edge between vertex 2 and vertex 4, which is 4, and the cost of edge between vertex 3 and vertex 4, which is 1. So the total cost of the spanning tree will be 2 plus 4 plus 1, which is 7. Therefore, different spanning trees will have different cost. So, given such a weighted graph G, we would wish to select or be interested to have a spanning tree of minimum cost. A minimum cost spanning tree of a graph is a spanning tree of that graph that has the least total cost. Therefore, the minimum cost spanning tree problem is a minimization problem. And since the identification of minimum cost spanning tree involves the selection of a subset of edges, this problem fits the subset paradigm. One important point to remember is, if edges have equal weights, the minimum spanning trees may not be unique. But if the weights of the edges are distinct, then the minimum cost spanning tree will be unique. There are many other applications of minimum cost spanning trees. For example, problem of connecting all the network devices using least amount of cables. Therefore, for a graph, they can be different spanning trees. But what we need is a spanning tree with minimum cost, and this tree is also known as minimum cost spanning tree. So, to construct a minimum cost spanning tree, we use a greedy method. The greedy method is to construct a minimum cost spanning tree edge by edge. The optimization criteria is to choose an edge that minimizes the increase in the sum of cost of edges already included in the spanning tree so far. The constraint is the selected edges must form a tree, and they must be n-1 edges for an n-vertex graph. There are two approaches of constructing a minimum cost spanning tree using the greedy method. The first approach is the Prim's algorithm. The other approach is the Kruskal's algorithm.